All right, in this video we're going to look at the composition of functions. And function composition is when the output of a function depends on the input that is itself an output of another function. In other words, we're going to take a function and we're going to insert that into the value for x of the other function. So in our first example, there are actually two ways that we could do this, just like there was two ways that we could do the combination. There's two ways we can do the composition. So I'm going to show you both ways, and you do the way that's easy for you. All right, so the first composition that we're going to do is f of g of 4. Basically what this means is that I'm going to take my function g and I'm going to plug the number 4 into x for that function. I'm going to find the number and then I'm going to take that number and plug it into f. So the one thing you want to remember about function composition when you're doing function composition, whatever's inside the parentheses, you want to work that first and then work the next one. So you work from the center out, just like you do with PEMDAS. Work from the center out. So we're going to start with the center function right here, which is g of 4. All right, so when I do this first substitution, I get the number 18. So I'm substituting 4 in for x in my function g, and I get 4 squared plus 2, which is 18. Then I'm going to take that number and I'm going to plug that number into my f of x. All right, so I've taken my value 18 and I've plugged it in to my f of x, which is 2x minus 3. I've plugged in the 18 where the x goes, and I get the value 33. So in conclusion, f of g of 4 equals f of 18, which equals 33. Okay, so in the next way we can do this is the second way we could do this. I'm going to take my g of x function, which is x squared plus 2, and I'm going to plug that in for x in my f of x function, which is 2x minus 3. So I've taken this x squared plus 2 and I've plugged it in to f of x here and here. Then what I'm going to do is simplify this and then substitute. All right, so we have plugged in our x squared plus 2, simplified it, and we come up with 2x squared plus 1 as our f of g of x. Now what I'm going to do is substitute the 4 in for this function that we've created, this 2x squared plus 1. I plug the 4 in, and I get, when I simplify this, I get again 33. So whether you substitute in individually and then do the combination, or whether you do the combination and then do the substitution, you should still get the same result. Which way you do it doesn't matter to me. Just do whatever's easy for you. One of the things we need to talk about is the domain of a composition. In the domain of a composition, any domain restrictions that we have for g of x are also going to apply to f of x when we combine or make a composition of these two functions together. So one of the things that we have to do is we have to check for any domain restrictions that we might have within our functions before we actually make a composition of them, because these different domain restrictions are going to affect both of the functions when we do the composition. That's basically all this means right here. Okay, so let's take a look at this notation for compositions. You have two different types of notation, and these notations mean exactly the same thing. This O right here, this is not the word fog. Okay, let's get that straight. This means f of g. Basically what this means is that I'm going to take g and I'm going to put that function inside the function f. So f of g of x means the same thing as this. F of g of x. And we say it the same way. So don't think that this word is fog. That is not the word fog. F of g. Same thing here, we have g of f. We're going to take f and we're going to put it inside g. So g of f of x. This means I'm taking my function f of x and I'm going to substitute it into the x for my function g of x. So let's look at some examples. All right, so first we need to determine what values of x are included in the domain for each of our functions before we start combining them. In the first function, we have f of x equals 2x plus 1. That's simply a linear equation, and it's a polynomial. So in polynomials, x values are all real numbers. So in this particular domain for f, we're going to say that the domain is all real numbers. In G, however, we have a restriction. This value for x right here cannot be negative. So x has to be greater than or equal to 0. So we need to make sure that we determine these domains before we start doing our combination. All right, so our domain for the first function is all real numbers, or negative infinity to positive infinity. And the domain for the second function, g of x, is going to be 0 to infinity, or x is greater than or equal to 0. Okay, in this first example, it says compute f of g and find the domain. So I'm taking g, which is square root of x, and I'm plugging it into my function f. And I get 2 square root x plus 1. And so I need to find the domain of this. Well, the domain of this is just the same thing as the domain of g of x, because remember here in this radical, x cannot be negative. So our domain for our new function is going to be the same as the domain of g of x. Now let's look at g of f. All right, so for g of f, we have a different situation. Inside here, the domain could be all real numbers. However, as soon as we plug in our f of x into our g, which is a radical, this changes. We know that this number right here cannot be 0, or not less than 0. This number cannot be less than 0. So we need to set this equal to 0 and find out what that number needs to be. Okay, so I've solved for 2x plus 1 equals 0. So I know that my value for x cannot be negative 1/2 or anything less than negative 1/2, or my function is not going to be a real function. So my domain is going to be all real numbers greater than or equal to negative 1/2. Okay, so as you can see, the domain can change depending on what it is we are plugging in to our functions and where. So you always want to check to make sure that any value you put in for x in one function isn't going to have this domain restriction on the other function. So that's one thing that you're always going to have to check. So in summary, finding the domain of a composition. To find the domain of a composition, f of g of x. First, find the domain of h of x, which equals f of g of x, in the way you would find the domain of any function. Second, restrict the domain you found in step 1 by keeping in mind that g of x must also be defined over the domain. So let's take a look at some examples of this, and so you can understand a little better what this means. All right, so on the next page, you've got these two functions, f of x and g of x. And the first thing we need to do is find the domains of the two functions first. So let's do that first, and then we will look at the compositions. All right, so the first thing I did was find what value for x would give me a 0 in the denominator. I know that for this function, that this value under the denominator cannot equal 0. So what I want to do is I want to find the value for x that will make this piece right here equal 0. So what I do is I set this equal to 0 right here, and I solve for x. And when I do, I get that x equals 1/5. So when x equals 1/5, I get a 0 right here in my denominator. So for function f of x, x can be all real numbers except 1/5. And the way we write that domain is negative infinity to 1/5, and then open parenthesis, because we don't want to include the 1/5, or parenthesis 1/5 to infinity. So basically this domain right here tells me that x can be any number except 1/5. Now in g of x, I have the same situation. X cannot be 0. This cannot be 0. So I have the same kind of domain here, except instead of a 1/5 for g of x, I'm just going to put in a 0. All right, so here I have negative infinity to 0, open parentheses, or open parentheses 0 to infinity. So this would be my domain for g of x. Now what happens when we do the composition? Now in this first composition, I'm doing f of g. That means I'm taking g and I'm going to place it into x. Okay, so here's my composition. I've taken my function g, which is 1 over x, and I've placed it into my function f of x. So what I end up with is this right here, 4 over 1 minus 5 times 1 over x. So now I need to simplify this. All right, so this might seem a little complicated, but I'll try to walk you through it slowly. If you don't remember how to manipulate rational functions, I'm going to take it a little slow. If you have any questions, please make sure you ask them in class. All right, so what I've done is I've taken this and I've simplified the denominator. I made this 4 divided by 1 minus 5 over x, because 5 times 1 over x is 5 over x. Then I took this 1 and I changed it to x over x, because this is a number 1 and this is a fraction. And in order for me to subtract a fraction from a whole number, I need to change that whole number to have a common denominator with this fraction. So I changed the 1 to be x over x. And that's what I get right here. X over x minus 5 over x. And then I simplify it again. I get 4 over x minus 5 over x. Now I have a fraction divided by a fraction. So what I have to do here is I have to multiply the number 4 by the reciprocal of this fraction. So I get 4 times x over x minus 5. I basically just flipped this bottom fraction over and multiplied. Now my final answer is 4x over x minus 5. And what I need to do with this combined function is I need to determine what the new domain is going to be. Well, the domain cannot be the number 5, because if I get the number 5 right here, that gives me a 0 in the denominator, and that makes this function undefined. So now I have a new domain. First of all, x can't be 0. Second of all, x can't be 5. So the way I'm going to write that domain looks like this. Okay, The domain is negative infinity to 0, or 0 to 5, or 5 to infinity. So this says that x can't be 0 because here we have an x in the denominator of our first function. That can't be 0. And that x cannot be 5 because if x is 5, then we have another 0 in our denominator. So that's the result for our domain for this function f of g. Let's take a look at g of f and see what happens. All right, so I've taken my f of x, which is 4 over 1 minus 5x, and I've plugged it into g. That gives me 1 over 4 over 1 minus 5x. So this would be 1 over x, but I've replaced my x with this other function. Now I'm going to simplify this fraction. Okay, so in this case, I have a 1 divided by 4 over 1 minus 5x. So what I do is I multiply 1 times the reciprocal of this fraction, and I get 1 minus 5x over 4. This ends up being my g of f. So in this case, my g of f could be all real numbers because I don't have any restrictions on this fraction. X could be anything. So in this case, the restriction is only limited to what the restriction is for this part of my composition. So in this part of my composition, x cannot be 1/5. So in my domain, I'm going to show that x cannot be 1/5, but for this part of my function, x can be all real numbers. So this is how my domain is going to look now. Okay, so for this combination, my domain is going to be negative infinity 1/5 or 1/5 to infinity. Now what would happen if I wanted to put g inside of itself? This is what it would look like. Okay, so I'm putting 1 over x inside g of x, which is 1 over x. So it's just 1 over, and then here where the original x was, I'm putting another 1 over x. So I'm going to simplify this now. Okay, so I multiply 1 times the reciprocal of the denominator, which is x over 1. So 1 times x over 1 is just x. So my g of g is just going to be x. Now in this case, my result could be x could be all real numbers. However, we still have to remember that the original g that we plugged in, x could not be 0. So that domain is still included. So we still have to state that x cannot be 0 in our domain. So as you can see, even though the resultant function from a composition might be that x can be all real numbers, we have to take into consideration the domain of whatever it was we plugged in the first place. So when you're checking for the domain of your resultant function, make sure that you're checking the domain of whatever function it was that you substituted into the original function, because that is going to have an effect on the final domain that you write. That's all we have for function composition. In class, we're going to do some practice problems from the book, and if you have any questions, please make sure you ask during class so that I'll be able to answer any questions you might have. Okay, so looking back at what we've done so far, up here where it says, for example, B, right here, it says 1/5. This should have been infinity. Go ahead and fix that on your notes. This should be infinity, not 0. So let me just fix that real quick. Okay, and that's it.